All right. So, all right, so there's specific things for students, I understand that, but in general, I think maybe it comes across that I do love math, and I love what I do. Calculus is like where math starts. I don't think I've even told you that yet. I don't like to tell any student that until they actually get to calculus. But I think I said something like this on the first day, because you feel a lot of responsibility on your shoulders as a teacher when you're teaching calculus, because it's like the underpinning of everything else. It's the underpinning of stuff that you've done before that you just never saw the proof of. So later you'll learn all these proofs for things you've done before and go, oh shit. So then you realize calculus has always been there. But I don't want you to feel like, I don't know if I'm just having myself a rough time this semester. I always want students to feel comfortable asking me anything. Obviously in class I have to time manage, like I said, right? You guys might just be naturally quiet people. Some of you guys speak up, but not everybody, which is fine. Then come see me in my office. We can be nice and soft and quiet and talk about stuff, right? I can't force anybody to do anything, but I do want you to be aware of all the stuff you can do. The fact that there were like no A's on this test does disturb me, but you know, some people didn't do like bad. I mean, good high B's. I wish there would have been some A's, but I'm not going to curve it so much that I just artificially create A's. Anybody ever taken statistics? Any statistics? Standard deviation was really small, which means the mean wasn't where it was because there were really extreme low grades. Standard was so small, so it seemed like, and I didn't feel like I graded it hard, so it felt like it was where it should be. So I did curve it, but not to artificially create A's. You guys understand? Okay. All right. So we'll try to move on. And I also want to say, I am the first person to accept that maybe I'm not explaining things well, or whatever, right? Feel free to come talk to me in my office about whatever. I hope to God with my handouts and the homework I assigned and the lectures and everything that will come together and make sense. Is my hope. Okay. All right. This one last section, chapter 2. We'll start off with like the visual component of it, and then we'll get into the specific computational part of this. So if I have a graph, I've sort of done stuff like this with you guys already. The cubic graph gets used a lot for this. How do I know that's a cubic graph, like some x cubed somewhere? It touches the x-axis at 3 points, right? It could only touch it once if I picked it up and pulled it up here. So what's more important than that? That's a good observation, but what's even more important than that? It has 2 turning points. Do you remember from pre-calculus? If you had an x to the 7th, what's the most turning points you could have? 6. Right? X squared has how many turning points? 1. X cubed has no turning points, but if you start throwing some other terms in there, it can have at most 2. X to the 4th can have at most 3. Those are the kind of ideas that sometimes get glossed over, but they are stupid useful, right? And yes, I use the word stupid as an adjective too much, but they're really useful. Anyway, so my question to you, the question I put on the test was, where is f prime less than or greater than 0, depending on which version you had. Right? So some of you guys had, where is f prime less than 0? Some of you guys had, where is f prime greater than 0? And I think that was number 2 on part 1. So obviously, where is it less than 0? This side, the middle, or that side? Where's the f prime? What does f prime mean? What does f prime of x mean? Slope. So really, when I say where's f prime less than 0, where's the slope negative? That's the translated into English. So a big part of a lot of math problems is take the question they're asking and translate it into English. That's why a lot of people have trouble with math. It's because you have that translation step that we skip. So when I say this, that is saying where's the slope negative? Where's the function going down? Take it even further down to even deeper into English, right? So that would be from here to here, right? So if this was -2 and this was 1, for example, the answer would have been from -2 to 1. Now what's it doing at -2? What's the slope at -2? 0. And what's the slope at 1? 0. 11. So if it is a turning point, obviously the slope at that turning point must be 0. That's by definition. Here the slope is negative. Here the slope is positive. So in the middle it had to have been 0 in order to make that from negative to positive. Does that make sense? I like it. So what I'm about to do goes beyond this question. But it does kind of include the idea of that question. I'm going to plot in blue, and this is what you guys are going to do in a bit on this worksheet. I'm going to plot what f prime looks like on top of the f. And really the best place to start is where is the slope 0? So I'm about to plot the values of the slope. This is a really difficult thing to do because your brain starts to balk and you end up just following the function. So watch this. At -2, what is the value of the slope? 0. So I'm going to put a point at 0. That blue dot represents the value of the slope at that point. So of course I'm going to put right here another point. I like it. And now what is the slope back here? Really big? Positive, right? It's really big positive, but it's getting... It's a really big positive, but it's getting smaller. It's getting closer to 0. I love it. So how am I going to graph that in blue? So at this point, it's really big positive. And then as I move towards -2, it's less and less and less and less positive until it's 0. So the closer I get to -2, the closer these values I'm plotting should get to 0 because the slope is getting really small. The slope is getting really, really tiny. So why is this blue one way up here? Because that represents the slope at that same point. The slope is big positive. So where am I going to plot it? Frickin' big positive. No, yes, sir.
So is that how we would go about graphing it then? Like,
yes, that's it. So start at what I call your anchor points. And then just start filling in. Well, if it's positive, it's going to be up here. Now, what did we say about between these two? We said that that's where it was negative. So look, this kind of makes sense. It becomes negative, doesn't it? And then it gets bigger and bigger negative. But what happens about right here? So it gets bigger, it gets more and more negative slope. Do you guys see that? And what happens about right here?
It's smaller.
Yeah. So it gets really, it's negative here, but it's getting bigger and bigger negative, until about right here, let's say. That's where it starts to turn the corner and start to come back up. That's a point in the economy. They often say in the news something like the rate at which the economy is decreasing is getting smaller or something like that. Oh my God, that's a freaking second derivative. That's like a slope of a slope. So right here, that's the biggest negative slope. So that should be where it's the deepest. That's the biggest negative slope right there. And then the slope starts to turn around. Still negative, but less negative. So if your economy's tanking, you're hoping to God you hit that point. You're like, all right, it's still going to go down further, but at least we're like going to start to turn around, hopefully. So you hear this kind of thing in the news all the time. They talk about second derivatives all the time. The news don't even realize what they're saying. And of course, it's going to get less and less and less negative until it hits 0. And what happens after this point? Big positive. I love it. Notice something that's going to come out later today. What was the original function? It was like x cubed, right? Blah, blah, with other terms. And what's the result look like? X squared. I love it. Kick ass. Let's do another one. Yes, sir?
What is this concept called?
Plotting slope. Given f, plot f prime. Yeah. So it's like derivative curve sketching, if you want to give it a more formal title. All right, let's do another one. Let me give you what's affectionately known as the butt graph in pre-calculus. If you have no idea what I'm talking about. Anybody know what that would be, roughly? You guys, if it never came up in your pre-calc class, I'm sorry. Could be other things, but oh. This is roughly what?
Negative x to the 4th.
I like it. Negative x to the 4th. It kicks ass. So that's like the end behavior, right? It's down on both sides. I like it. It's got extra little shit in the middle because it's got extra little terms out there. How we doing so far? So where do I start? If this is f of x, and I need to plot f prime, what do I first plot? The points were 0. The points where I have a horizontal tangent line. Let me say that again, because you're going to see this a lot in homework the entire class. Horizontal tangent line. Those are key points, aren't they? If this is a profit function, I want to be at that horizontal tangent line. Because that would be the max profit that I could make. So finding the horizontal tangent line locations becomes huge. Okay, so here, there's a 0. Where else? Like here is a 0, right? And then here is a 0. So plot those first. And then you start to see, you got to keep your brain going the right way. You can't let it take over. Because like I said, you'll start to do this. If you do these problems, your brain will just start to follow the function. You're like, stop it. Because what is the slope here? Is it positive or negative?
Positive.
It's positive. So where am I going to start to draw my blue?
From the top.
Up here. Big positive, getting smaller. Big positive, getting smaller. And of course, what happens past this point? Yeah, it gets bigger and bigger negative. And where's that point? Can you see the point in the middle where it's the biggest negative slope? So like here, it's 0 again, and then it gets more and more and more negative, but at some point it's getting less and less negative, right? So about right here, maybe. Later, we're going to call that the inflection point. That seems to be, it makes sense somehow. That's the inflection point. Right now, it's not all that important to know that, but I might as well tell you that now. So that should be the deepest place this goes, because that's the biggest negative slope. So I just make sure that, okay, this is going to be deepest part right there, and then I come back up. Because again, what's happening after that point is getting less negative, and now it becomes positive. And this is where it sort of follows the graph a little bit. But when do I have to come back to 0 again? Right here. So you get positive, and then can you find the inflection point location? It looks to be about in there somewhere. So later, of course, thank God, we're going to calculate that exactly. Right now, you just sort of eyeball it, right? So right there should be the highest point, and then I got to turn around because now I'm getting less and less and less positive. And after that, of course, I just go crazy. Crazy, big, negative. Wow. So look, again, the original was a negative x to the 4th. Anybody know what this is? Negative x cubed. I love it. It seems like they're always off by 1 degree. Niftedelic. Okay, I like it. Oh, okay. So we got. That is something that will take a few attempts to really get it down. Something's got to click in your brain. But you just keep making sure wherever you are drawing, you make sure it's matching what the slope of the original is at that point. That you just got to kind of keep on yourself. You can't just kind of flop this out and go, yay, no. Okay. So that's kind of like a visual way to find a derivative for a function. So I just want to bring this word up. Differentiation is the process of finding the derivative. So whenever you see this word differentiate or differentiation, it's talking about the process or use the process of finding the derivative. And the derivative, again, is the slope. I love it. So a quick aside, just while I'm thinking about it. If I said, you don't even know this yet. If I said, what's f prime if f is that? Yeah, you translate that as, what's the slope of f? Well, it's a freaking straight line. I don't need no calculus shit for that, right? So whatever rule we come up with for polynomials, better do this, or we got to throw that frickin' rule out. We already know what the slope of these are. Quotations. What about this?
0.
Yes, it's 11. I love it. So the derivative of any constant, it's got to be 0. Because how much is a constant going to change? Well, it's not. It's a constant. That's the definition. It's not going to change. So the rate of change better frickin' be 0. I like it. Okay, that was a little aside. That's why I put it over there. So, differentiable. So you're going to have some problems that say, where is a function differentiable? Another way to say that is, in order to be differentiable, you have to be able to find the slope at the point. So if I say, is it differentiable at x equal a? So here's an example of a function that's not differentiable. At a. Got it. So my best example of what this really represents is that's a plane you don't want to be in. Right? We're going 5. We're all dead. You can't survive that shit. Right? This is officially called a kink. Why do you think that's not differentiable at that point? In order to be differentiable, so how do we start talking about derivatives? We started talking about finding the derivative at a point. And that should be the slope of the tangent line. And you can always, if I give you a nice curve like this, you should always be able to kind of draw an approximate tangent line, right? Just kind of go, what's the slope doing right there, and just kind of continue that forever.
Is it because there's there's no curve, so it would just go from positive to
yeah, what would it would go, oh. All right, so that's one thing. I love it. That's exactly the first way to look at it. A more detailed reason is you're differentiable at points where the slope is continuous. What's the slope here? Positive something. And then it instantaneously becomes negative something. Right? So say the slope, if I'm going to draw the slope, okay, stay with me. What would the slope look like up to A? What's true about this? What's the slope doing? Is it changing? No. It's just always positive, so it's whatever that is. So say it's positive 3 or something. You guys with me? And then what happens after A? It's suddenly negative. So is the slope continuous? No. So that's why any kink like that, any instantaneous big change in velocity, in slope, it's not differentiable there. And what are slopes based on? What are derivatives based on? Limits. So that's sort of why the limit from both directions doesn't agree. That's why it's another way to look at it. It's not differentiable at the point. Somewhere else that it's not differentiable at would be a little more harder to tell. There's a point here where it's not differentiable. So what's another way you could have a limit not exist besides it doesn't agree from both sides? The limit could go to infinity. What's the limit? So what's the slope doing? It's getting bigger and bigger positive until right here it's freaking infinite. Do you guys see that? And then it comes back down. So if I graph the slope for this sucker, it's going to be small, and then it gets big, and then it gets insanely big right there, and then it comes back to normal. So that's also where the slope is not continuous. So I never had a teacher say it to me like that, but I eventually realized differentiability is just continuity of the slope. If the slope suddenly changes some crazy drastic way somewhere, it's not differentiable there. Yes?
So if your graph's continuous, is it different?
I love it. If it's differentiable, it's continuous.
But not the other way around?
Yeah, not the other way around.
Okay.
No. Differentiability is a harder test to pass. Because these are both continuous. Everywhere, right? But these are both not differentiable at A. I like it. Kick ass. In fact, there is a theorem that says that. Oh, where are you? Well, I'm not going to find it immediately. It's somewhere in here. Anyway, so if it is, here it is, Theorem 4 at the bottom of page 156. If f is differentiable at A, then f is continuous at A. And there's logic issues. We all have logic issues. If this, then that does not mean if not this, then not that. Right? If it isn't differentiable, does that mean it's not continuous? Well, I got two examples that go against that shit, so you guys kind of with me? So if you took a logic class, you might be a little ahead of the game with some of these theorems. Okay. So let me give you this. I'm going to try to, I talked about most of the ideas. I'm going to leave one of these open to you to figure out. Isn't that nice? I would love it if you guys worked on this together. But you don't have to. So the section, the side that's 2.8. The other side's all about chapter 3. We ain't there yet.